Hello, I'm Lenora Clark, Director of Autonomous Driving and Safety Technology. My team and I have created a series of short webinars to educate you on various materials used to build electronic hardware, the hardware that supports advanced safety systems in automotive. Throughout the series, we'll look at designs from a perspective of the printed circuit board manufacturing, assembly materials, and materials used to enhance semiconductor packaging and IC substrate designs. I invite you to think of the parts of these builds and how they affect the system overall. As we travel this web series together, I'll be your tour guide. I'll show you some cool things from a materials perspective, but ultimately you know your designs. You understand the challenges associated to them, and you know the final performance expectations. You will choose the appropriate materials to deliver success in your product. But to help you achieve the next level autonomy, I'll supply some materials data which I expect you'll be able to relate to your designs. In the discussions, I will focus on three areas: form factor, performance, and reliability. Today, I'll showcase a conductive die attach material for improved thermal management and increased product life expectancy. I'm excited to review this topic with you. When we think about computers or smartphones, we often talk about processing power. Well, now we need to talk about processing power for the systems in our vehicles. Basically, processing power is the ability to calculate information or instructions. Your phone can process over 3 billion instructions per second. A self-driving vehicle needs a supercomputer or really smartphone processing capability for its decision-making. Now, safety systems, especially radar sensors and camera modules, are constantly sensing in real time. Consider the difference in the camera requirements from your phone to your car. With a phone, you take a few pictures, maybe a 3-minute video of the dog snoring, but the car camera will be working the entire time that you're riding. And if we transition to a rideshare platform, the vehicle and its systems are functioning many more hours a day, potentially 24 hours a day. It's an immense amount of information to process. The radar sensor is the same. It's constantly gathering and interpreting information from the vehicle's surroundings. I like to think of the components in the design as the brains of the system. It's the job of the IC substrate packages, specifically for radar, to send and receive a signal. The information gathered is about the surrounding object's distance and speed. And more information on this design can be reviewed on a separate webinar recording, which focuses on 77 gigahertz radar designs. But that package we're talking about is called a MMIC, or monolithic microwave integrated circuit. For 24 gigahertz designs, the system used a quad flat pack, or a lead frame package. It had a low I/O count of about 32, and the silicon die was connected to the metal lead frame. As we transition to 77 gigahertz designs, these systems deliver greater resolution, and they're able to do that by changing the package to a ball grid array, a substrate-based package. The higher I/O count is now 200 pins. An I/O count is a number of connection points to the printed circuit board. More connections allow for faster information travel. The BGA MMIC has 5 to 6 more times connection in a smaller footprint than the quad flat pack. It's processing more information with greater power, and it's going to get hotter faster. In this image, we see the very hot silicon die at the center of the package. It's a thermal image on the left side. On the right side, we see how the die is attached to the lead frame or substrate. In this image, the red is the silicon die, the gold or yellow is the lead frame package, and the purple represents the conductive die attach. The industry uses a conductive adhesive in many cases, but the silicon die is the portion of the package that's getting the hottest. If we can provide a material that improves heat dissipation of the die, we can extend the package life. A conventional epoxy adhesive offers very little thermal dissipation. People moved to a silver-containing adhesive, but with the amount of processing occurring today, it's still not removing enough heat. We offer a hybrid of the two. It is an epoxy that has a higher concentration of silver flake in it. The more densely packed silver after thermal cure results in greater thermal transfer. We specifically measure this through thermal efficiency. So you can see from the chart, a conventional epoxy is on the order of 5 watts per meter Kelvin. Our Atrox material is closer to 12 watts per meter Kelvin. To deliver faster systems with greater information calculating, advanced component packages are required. Extending the life of these packages in turn extends the life of the system and delivers enhanced reliability. Our line of Atrox materials will help you reach improved performance and increased life in your package designs. To make advances in your technology, you will need advanced materials that match your life expectancy. We have over 60 years of electronics experience in all market segments. We specialize in the development of advanced materials, and we have a complete understanding of the expectations of the automotive market with a strong focus on harsh environments. I thank you so much for your time, and please don't hesitate to contact me if you have any questions or if there's another topic you would like me to consider for the next series of webinars. I look forward to continuing the discussion with you.